6 months before the World Cup 2014 in Brazil, and what happened when flow arrived and actually collapsed the building. But this is not the worst news for the Brazilian people. The worst news and disaster is that there's no game on that day. My name is Farshid Kardan. I'm currently working as a scientist at EPFL and wind engineering and renewable energy. And we conducted several CFD simulations, a project with Professor Bavril and Professor Fernando Portiagel. And today I try to just share with you some of our latest experience and latest achievement that we had. And we try to just adopt a kind of scientific attitude and find a way to show how we can go further with the urban physics. Because today I actually heard so many projects about the CFD, but in fact, I try to now explain the physics behind the CFD simulations. If you consider this building, and remembering the first slide, the stadium was just collapsed, what was the reason? The first reason probably is the turbulent inflow. But what is the turbulent inflow? So if you consider this building, once the wind flow collide the building or bluff body or any object, it creates a kind of complex and chaotic pattern just around and behind the block. So this is the large eddy simulation that we performed recently with the code that we developed at the Wire Lab. And as you can see, these patterns are quite sophisticated. And in fact, the turbulent flow, it contains a lot of energy. And there's no absolute solution for that. Right now, if you just Google a turbulent flow, you can probably find in Wikipedia that Nobel Prize laureate Richard Feynman described the turbulence as the most important unsolved problem of classical physics. That means that there's no absolute solution for that. But this is very complex, but if we go further and we check, and we have now several buildings, just please remind that these are the idealized buildings. So this would be more complex because each building actually had a kind of impact to the surrounding buildings. But what if we want to dream more? What if we want to simulate a kind of complex district like Manhattan, and have a kind of results having the simulation and having the variable of the interest. So this is a very complex task, and we believe that it's very important at the same time, because imagining that this schematic urban block, we'll see that there are so many phenomena actively are there, like the wind velocity with the wind profile, radiation, rain, humidity, and next to them we will have so many energetic challenge. For example, we can have the solar panels or wind turbines, climatic, security and comfort and design matter. And not to mention that there's a huge potential just there. All we need is the accurate and fast computational fluid dynamics. So we believe that if we can find a core for resolving the turbulence inflow and having a kind of model, CFD model, accurate CFD model, we can have an answer for each of these questions that you can see here. From natural ventilation, for the building scale problems, wind engineering, solar panels, snow transport, meteorological phenomena, even the pollutant dispersion that can be simulated with this core. So we believe that this CFD can have a solution for each of these questions, and it could be a kind of guide for the design decisions. As you can see here, for example, we just performed simulation at the early stage to have three types of high-rise morphology: the rectangular prism, cylindrical, and twisted. And we put it in a semi-idealized urban canopy, and then we decide to see, okay, what happened there? What is the pressure dispersion in these buildings? The same thing with the turbulence. We can understand where we can have the higher turbulence or better optimum turbulence for implanting the wind turbine. So I keep continuing on this. There are two main approaches for that. So we recently at EPFL designed and developed the approach to measure the airflow in urban environments. The first one was the light detection and rendering, called LiDAR. There's a laser machine that can analyze quickly the different variable of the interest. The second one is that we just finished to redesign the whole software and a part of the hardware of the drone. As you mentioned in previous presentation, that drone can be used for that. And we actually designed this drone and we had the results for that. And even we go further and we built several tower measurements at EPFL campus to understand clearly what would be the turbulence inflow and how we can actually measure different elements. So these are the approach for measuring, and now we want to claim some of the main approach to studying to study the airflow. So the first one you probably know about it is the full-scale measurement. And of course, it's not affordable for urban and architecture scale project. The second one is the wind tunnel. I'm pleased to just mention that at EPFL, we recently developed the atmospheric boundary layer wind tunnel closed circuit on a 1,000 square meter land. And these reduced scale of wind tunnel experiment can help us to validating some data. But most importantly, and probably the cheapest version, is the computational fluid dynamics CFD. But CFD itself has three different main approach: direct numerical simulation, large eddy simulation, and Reynolds average Navier-Stokes equation. So let me just get a little bit and show it in a scientific way. If you consider the structure of the flow, okay, according to the Richardson theory, cascade theory, all the turbulent flow starts with structuring the large eddies and then the cascade into the reduced scale and smaller scale. So in CFD, once we talk about the CFD, we want to talk about the DNS. DNS actually solve all scales of eddy, all eddy and including the larger structure and small structure. But it's maybe interesting that mention that computational is not really affordable. Recently, NASA published a paper, and they mentioned that probably for the architecture scale, we have to wait up to 2080, 60 years at least more. And then secondly, we go through the large eddy simulation. Actually, we recently developed and published two papers about the codes that we developed in LES. And we somehow proved that they are the fastest and most accurate for urban environments called wire LES. This could be somehow affordable, but still is very expensive. We need the supercomputers. Remember the movie that I show you? Those movies are extracted from our LES codes. And for the simple case one, we use supercomputers, high-performance supercomputers, without non-stop running for more than 2 months to just get that correct simulation and behavior. And this third one, which maybe would be interesting, and I imagine that my colleague in previous presentations uses that the Reynolds average Navier-Stokes equation. But this is not the end of the story. So recently, during this past years, I just forgot to mention, I found recently my startup company, Archiflow, and we had some collaboration with different architecture firms, including Foster's and so many research centers. And we finally find that the need is accurate, high fidelity, and fast CFD. And the main challenge in architecture and urban scale, first is defining the boundary conditions, and the other word, having and recreating the natural meteorological phenomena. And the second one is that having and evaluating and reducing the uncertainties in urban and architecture scale. So if I want to continue for the first step, let's say recreating the realistic meteorological phenomena of a city, we decided to work on mesoscale CFD. The main question that we asked is that can the local atmospheric boundary layer, for example, wind profile, temperature, humidity, the wind direction, be forecasted by CFD simulation? Just please forecast it. It means that we don't want to just study a current situation. We want to study the future. So that could be very interesting, especially if we want to build a kind of district or a kind of iconic building. But if we want to do this, since 2015, we started to work with the gigantic codes called weather research and forecasting codes. So the idea is that actually we get the meteorological data, we analyze this data, then we add the geographical data, and we do it for a very large scale. The good thing about the WRF, which is actually designed in 1990 in US, is that it's free for everyone, but it's not really user-friendly. There are just a bunch of codes there, and the other problem about it is that it's just designed for physical science, and there's no validation study about it. So we tackle this problem, and we start to have the validation, and we check the evaluation of the forecasting of a very complex, complex area in Switzerland, and we try to find the answers, the results. So what we did actually, in Juvent in Switzerland, there are 12 kind of small wind park with the 12 Vestas 2-megawatt turbines, and each of them has a kind of anemometer equipped with the supersonic sensors for having and measuring the weather condition and wind speeds. So what we try to do, we start to forecast the next months, next 28 days of that region, and we compare the results with the observation that we get. So I want to just give you a notion about the scales that I'm talking about here. So for doing this simulation, we get the data, observed data at the whole Europe. We're talking about the real big data here, the whole Europe, and then we start to run the simulation. Once we run the simulation with 30 kilometers grids, as you can see the bigger square, then we just narrow it down for Western European scale, narrow it down once again to the Switzerland, and then we arrive to just 370 meters. So what are the results after 1 month? As you can see here you can find the wind speed. This is just one example. Wind speed that we get from the simulation, and we compare it with the observation results. It's quite good, I have to say. And it's better specifically when we just compare the windrows for the wind direction to understand what is the wind direction. And we find out that the observation and simulation results agree fairly well. However, there are some differences, which is quite normal. We did this problem, and we found out that currently the resolution of geographical data are not really realistic. So the place that we actually, as you can see on the top part, the place that we simulate the topography is what you can see, and the data that we had is the figure on the bottom part. So this is just one part for having the mesoscale. We found out that there's a possible way to having the live and forecast for the global scale, mesoscale weather. And now the idea is coupling that with the architecture scale or urban scale simulation. So as I mentioned earlier, Just a quick, simple way to understand what is CFD. Today we talk about the CFD, but I'm 100% sure some people, they probably don't know what is really CFD. So the process of the CFD is that we design a geometry. If you're using the commercial software or codes, maybe you can use the Python for coding the geometry. Then we assign the mesh, which means the sensors. These are the sensors that actually we can understand and we can analyze the different variables. And then we set up the boundary condition. We try to recreate the weather meteorological condition. And then we run our codes, our turbulence model, for example. And once we get the results, we can understand and optimize according to our needs. So what we did, in fact, one of the things that we did is we developed the LES code. We developed as well a kind of RANS model code, and we tried to find most of the turbulence model using commercial software, more probably sophisticated software like ANSYS Fluent or CFX, or CC, or so many actually, there are so many. So we try to evaluate once again at urban scale and architecture scale, the standard K epsilon, K omega, RNG K epsilon, SSD model, and RSM for these two types. One other thing which is quite important is that the grid resolution. Once we talk about the CFD, these sensors, this mesh, we cannot have the fine mesh because computationally it's just not affordable to have a very fine mesh. It's not possible. So in larger scale simulation, we have to go to coarse simulation. And the other thing is that most of the softwares, again, once you have a bit of complex geometry, they try to have a kind of unstructured mesh. So we evaluate all these models for two different cases: idealized urban canopy, idealized single building, and 3 grid resolution and 2 grid structure. And we compare the results and validate the results against the wind tunnel experiment. Wind tunnel experiment and LES. And what we found was quite interesting. So here you can see just the domain that we use for a single building, isolated building, and then with the laminar inflow. And then we have this idealized urban case with turbulent inflow. So we use the turbulent inflow for just simple case that we got from the mesoscale simulation. And then 3 different resolution, as you can see here: fine, medium, and coarse resolution. And then we performed the simulation, and interestingly, we find that so the left column is the fine resolution, the middle one is the medium, and the third one is the coarse resolution. And we find that the commonly used, especially in commercial softwares, standard K epsilon and standard K omega model cannot properly reproduce the flow recirculation. It means that if you consider the recirculation center at the wind tunnel, the black buildings, there's a recirculation center, you'll see that these 2 bottom turbulence model, standard and K epsilon and standard K omega models, they cannot really properly reproduce the recirculation center. And that means that they're not only give us the wrong answers, sometimes they can completely mislead us in design decisions. So this is very, very important for us. If you go further, I actually find that as I mentioned, standard K epsilon, standard K omega models are completely out of the league. And the RNG K epsilon model, which is the new kind of advanced model, again, it shows that it's quite sensitive to grid resolution and grid structure. Especially for the resolution, you can see it means that this model that we can easily find in different commercial softwares, and they recommend somehow this turbulence model. For urban scales, they are quite sensitive, and they cannot really provide accurate answers for us. I, in fact, checked as well the pressure coefficient on a block, and we found once again that the pressure coefficient on a block just on top of the block for standard K epsilon and standard K omega model is not accurate at all. We checked the mean velocity around the building for both cases, not just only for the isolated cases. We just did this for the 3D idealized urban cases, as you can see here in a span-wise and vertical profiles. And we find that our model that we developed, the SSD, is a 4-equation model, SSD gammas, based on intermittency, Reynolds theta thickness, perform better and is almost close to our LES, which is the black line here, as you can see. So we keep this and we go further and we check the structure versus unstructured grids. And we found out that, again, these RSM and RNG models, they're quite sensible to this unstructured grids that we had. Most of, again, I want just to point it out that most of commercial softwares, again, they provide for complex geometry. What they do, they just put an automatic mesh, unstructured mesh, and this could be a real problematic for that. So it's probably not bad at the end. I mentioned about the computational cost. We performed this simulation and we find out that the Irwin's model, especially the one that we work, is at least 100 times faster than the LES simulation. As you can see here in detail, the numbers and the figures. So for conclusion, the first thing that I want to inform, that I want to just give this message to you is that the computational fluid dynamic is a simulation tool. If we can just have it in a correct way, in a proper way, as a tool for achieving the sustainable design, and we encourage the young architects to use CFD, high fidelity CFD, to study. And then the second part is that the meso scale and urban and architecture scale is very important to coupling these two models. Right now, the science, of course, the codes are gigantic. It's not really possible to handle with a simple computer, but we believe that this would be the future. This would be the future of the field, and now there are so many research labs which investigate and which invest in performing this simulation. So at the end, WRF has the potential for coupling with the smaller and micro scale simulations. Thank you very much, and at the end, I wanted just to show you our dream that it is possible to have the Manhattan in reality and having a high fidelity CFD for that. Thank you very much.